Welcome to lecture 13. I'm hoping to finish this discussion on nodal analysis and mesh analysis. Well, nodal analysis we did, but mesh analysis is very closely related, and I started this topic on Tuesday, so we'll do a quick review and continue from there. And so by the end of today, we will be done, hopefully, with the first half of the course, which is about basics of circuits and methods of analysis. And the second half of the course is what you would categorize under the topic of electronics in general. So right after the break, we will start talking about that. And so we'll start with diodes and continue on. But the main topics there will be diodes, op-amps, and transistors. And so it will become diverse. And one thing I'd like to emphasize is that once we start that, we will really heavily rely on everything up to this point. OK, so as I've asked before, I ask you two guys again to make sure you are not only familiar with the concepts, not only understand the concepts, but are fully fluent in using them. Because we will be switching back and forth between different ways of looking at circuits, but then with elements that are more sophisticated. And so we'll see interesting functionalities there. But to be able to understand them and analyze them, we need fluency in the first half of the course. So please make sure to review things, do the assignments. If you need to go back to some of the assignments, please do so. Use the office hours. And also, I'll post, again, some additional problems for your own practice. But it's really important that we treat the first half of the course by the end of today as something that we have to have completed, basically, right? Because the second half will rely on this very heavily. And so anyway, with that, let's continue. And so our topic today is continuing mesh analysis. And I'd like to start by describing the concept of mesh current again, doing a review of that. And here's how to think about it. Again, remember that ultimately the laws of circuits are KVL and KCL. And so they have to do with element voltage and currents. Now, in nodal analysis, we related element voltages to node voltages. And once we wrote our KVL and KCL in terms of node voltages, the KVLs became automatically taken care of. And so we just had to write KCLs explicitly. And that gave us equations in terms of node voltages that we put into a matrix form. In mesh analysis, we do the opposite. We change or we transform from element currents to what we call mesh currents. And by doing so, the KCLs will be automatically taken care of. And it will be our KVLs that will give us the equations to find the mesh currents. And then from there, we can go back and find element voltages and currents and power. So this is a quick review of what I said on Tuesday. And to think about the mesh current, again, let's consider an element. So an element has a voltage across it and a current through it. And then it's connected to some other things. And then it's part of some loops. And these loops, now if you look at a circuit drawn in a two-dimensional plane, the element could be on the edge, on the periphery of the circuit, and so it could be part of only one loop or one mesh, which is just a loop without anything inside of it, so just one simple loop. Or it could be somewhere in the middle and have two meshes on the two sides. Of course, you could have a circuit that you've made in a three-dimensional world, and it could have multiple meshes that it's part of, right? And that's fine. The concept will be the same. But so consider this element that's between these two nodes, and it's part of the two meshes that I've shown with dashed lines here. And what we are going to do here is to define this concept of mesh current, as I said before. And mesh current is not a physical quantity that you measure directly. The same way that node voltage was not something that you measured directly, but you were always measuring a voltage difference. Now, you had a reference somewhere that you defined for your circuit. And so the voltage difference between different points and that reference was what you called node voltages, right? Here, mesh current is not something that you directly measure, but it's differences in mesh currents that you measure. And so here's how the concept goes. That's the current I in the element, and that's a physical property. I could put an ammeter in series with this element right here and measure that current. You've done this in the lab. But we will define mesh currents, in this case, in the two meshes that the element is part of. Or I'm used to doing things clockwise. It doesn't really matter. It's just that. So I'll say that I have these two meshes here, and I'll attribute a current to each of these two meshes. And I'll call these capital I1 and capital I2. OK? Now, if I put an ammeter in this line here, I will not measure I1, nor will I measure I2. These are abstract concepts in my mind. I will measure I. But the way I define these is I equals the difference in these two currents that I imagine are circulating in these two meshes. OK? So I have I1 circulating in this lower mesh, and I2 circulating in the bigger mesh, or the upper mesh, sorry. And I is the difference of those. Here's one way to think about it. Imagine I1 represented the flow of a number of positive charges going in the clockwise direction in this full mesh. And so they're also going through this element here. And imagine I2 similarly being the flow rate of positive charges going clockwise in the upper mesh. So if you now zoom into this element, you will see that due to current I1, there is a bunch of charges, positive charges, going from left to right in the element. And due to current I2, there's a bunch of positive charges going from right to left. And so that's how to visualize that the current I is the difference of those two currents. And by the way, we know that it's really electrons that move, right? The nuclei are fixed. But by convention, over the past century or longer, we look at charge as if it's flow of positive. Current as if it's flow of positive charge. But anyway, so another way to think of it is maybe you think of this as a two-lane street. So if this is my element, if I represent my element like this, or let's say if this is my element, it's as if I have a current or a flow of cars going through it like this. So this is I1. And then another one going through it like this. So it's in this direction, I2. And so the net flow, so if you have 5 cars per second going from left to right and 3 cars per second going from right to left, the net flow from left to right would be 5 minus 3, 2 cars per second. So this is an abstract concept or a tool so that you can represent the element current in terms of these mesh currents. And you can see in a very simple way that once you do this and you draw a circuit that has a bunch of meshes connected, your KCLs will be automatically taken care of, because you have all these mesh currents going in meshes that surround each node. And so the sum of all of these will add up to 0, or the sum of all the element currents written as a function of these will add up to 0. So again, this is an abstract concept, so you have to visualize it like this, but it's a very useful one. It might be a little harder to feel it compared to node voltages, but it's really the same type of approach. One thing I want to emphasize again is that the direction of these currents that I've chosen, again, is my choice, my convention, and these arrows have nothing to do with my KVLs, which way I want to write my KVLs, clockwise or counterclockwise. That's a totally separate thing. KVLs are equations that have voltages of the elements in them, right? So if I have chosen my mesh current here to be in this direction, it does not mean that to write my KVL, I also have to go in this direction. I can go in the opposite direction, because all it means is that the order of the terms has changed in my equation. Okay? So more opportunity to be confused, unfortunately, with directions. But you know, that's life. But it also means, please, if you feel that you're getting confused with directions, try to catch it sooner than later and come talk to me about it. So then the element, definition of mesh current is such that the element current, in this case, is the difference of the two mesh currents. And by the way, if I had, for whatever reason, preferred to choose the direction of I1 as I have it here, but I2 the opposite direction, counterclockwise, then what would my element current be? If I had I1 the same way, but I2 the other way, what would my element current be in terms of mesh currents? Yes? You add them up. Great, thank you. So yeah, that's it. All right, so the rest is really doing examples, and so I have prepared an example here. And I had another example in the previous lecture, so make sure you watch that. Sorry, before doing the example, let's remember the steps then. Define mesh currents for mesh analysis. Define mesh currents. By doing so, KVLs will automatically be taken care of. And so, KCLs will be taken care of. And so write your KVLs. Now, in KVLs, you have element voltages. And so you use the element relationships to write the element voltages in terms of element currents. For instance, V equals Ri. And then element currents in terms of mesh currents. Right? Use element relationships to write element voltages in terms of element currents, and then element currents in terms of mesh currents. So a very similar approach to what we did for nodal analysis. But now what you're using explicitly is KVLs. Now, for resistors, this is very straightforward, because V equals Ri, and then your little I would be written in terms of mesh currents, as we just saw. But what if you had in the mesh that you're writing the KVL for, what if you had a current source? So you'll end up having the voltage of the current source in that mesh, in the KVL there, right? How do you relate the voltage of the current source to its current? To its current. Yes. How do we relate the voltage of a current source to its current? What's the relationship between the voltage of a current source and its current? There is none. You don't, right? So then you end up, if you have a current source, independent or dependent, you will end up having the voltage of the current source in your KVL that you cannot write in terms of mesh currents. So that introduces an additional variable. But that's fine because the information that the current source provides, namely its current, then gives you also an additional equation. So very similar to what we saw in nodal analysis, but there it was voltage sources that created this little bump. Here it's current sources that create this little bump. But they also provide additional information, hence additional equations, and there's no problem. So we'll see that in example, but I'll write it down. If you have a current source, be it independent or dependent, in a given mesh, you won't have a direct way to write its voltage in terms of currents. So you end up with this voltage as an additional unknown. But that's okay, since the information from the current source namely its current, will give you the extra equations that you need. Will give you an additional equation. So to get a feel for this, we have to see it in practice. So last time I did a smaller example, but here I want to do a bigger example that has this kind of thing in it also. So find the mesh currents for this circuit. And here's the circuit. So let's say this is a source voltage, a known value Vs, and this is another source, a current known value, and R1, R2, R3, R4, and R5. And this one, so let's call this V4. And this dependent source that I have here, it will be a voltage-controlled current source. So the shape tells you that it's a current source, and it's dependent. And the value of that current is alpha V4. So alpha is some parameter multiplying the voltage of the R4 resistor, giving you the current in that branch. So I'd like to find the mesh currents here. And I'll just follow the steps that we just talked about. So first things first, let's define some mesh currents. Now, how many meshes do I have here? 1, 2, 3, 4. These loops that are empty inside, each of those is what we call a mesh. And so I define an I1, an I2, an I3, an I4. And so these are my mesh currents. I could have defined some of them as going the other way around. That would have been fine. But I prefer, again, not to introduce too many opportunities to get myself confused. So I'm used to doing things maybe in one particular direction. And again, as we discussed, the KCLs will be automatically taken care of. Yes, KCLs will be automatically taken care of. So we have to write the KVLs explicitly. And for that, we need to define element voltages, because that's what we have in KVLs. So let's go around the circuit and make sure everything has, every element has a voltage assigned to it. So let's call this V1, V2, V3. We already have V4 defined. V5. And now the voltage of the source Vs is well defined. That's Vs. But I also have two current sources for which I need to define voltages. So let's say for this Is, let's call this V6. And for this other one, let's call this V7. Okay? So again, please be very careful. This is the kind of thing that I get questions about, which is, well, you know, you see alpha V4 here, and it's a natural human tendency to assume that V4 has something to do with the voltage here. But that has nothing to do with the voltage. Alpha V4 simply means the value of the current of this dependent source is alpha times the value of the voltage of this other resistor here. Okay? It's very important to be careful with these. So then the voltage defined for this element between the two sides is V7. So let's write the KCL, the KVLs. So KVL in mesh 1 Now, I also like to go clockwise for my KVLs, but you don't have to. But for me, it's minus Vs plus little V1 plus little V3 minus V7. Mesh 2 minus little V1 plus V2 minus V6 equals 0. Mesh 3 minus V3 plus V6 minus V4 equals 0. mesh 4. Maybe let's say plus V7 plus V4 minus V5 equals 0. That's my KVLs. The next step is to replace these voltages in terms of the element currents and eventually the mesh currents. So now if you look at V1, for instance, little V1, if I had this element current, little I1 here, little V1 would simply be R1 I1. But what is little I1 in terms of big I1 and big I2? Going back to the definition of mesh current that we just talked about. So look at this. And now here, little I1 in terms of big I1 and big I2, what is that? It's an example of that. You see, thinking about that example with cars in a street or positive charge, so I1 is in the same direction as I have defined little I1, and I2 is in the opposite direction. Okay? So that's that. And so now I have replaced the voltage, little voltage V1 as R1 times big I1 minus big I2. And then I'll do the same for all the other voltages. So doing that, for my first equation, I have minus Vs plus R1 I1 minus I2. This is what we just talked about. Plus V3, which you can do in the same manner. Imagine you have a little current I3 here. So your V3 is R3 times little I3, which, now what is little I3 in terms of mesh currents? Well, you have the mesh current I1 going in the same direction, and the mesh current I3, big I3, going in the opposite direction. So there you have V3, which is R3 times I1 minus I3. And finally, minus V7. Now, how do I relate the voltage V7 to any of these mesh currents, I3 or I4? Or, sorry, I1 or I4? And the answer is, I don't. So I have to stick with V7 for now. I have to keep it there. So that's my first equation. Then the second one, minus V1, so minus R1, I1 minus I2, plus V2. Now, what is V2? It's R2 times this current, I2. But what is the current I2 in terms of mesh currents? It's just big I2. Element R2 happens to be part of only one mesh. It just happens to be like that. So in this particular case, the mesh current I2 is the same as the element current little I2. So in this particular case, the mesh current actually does equal a physical quantity. It's not a physical quantity in itself, conceptually, but it happens to be equal to the element current I2. Okay, it just happens to be equal to that. But anyway, so little I2 is just equal to big I2. It's I2 minus 0 if you assume that you have another mesh, but there's no current there. So it's just I2. And then I have minus V6, and V6 is the voltage of a current source. So again, no way to directly relate it to the currents. So that's the second mesh. The third mesh gives me minus V3, which is minus R3 times big I1 minus big I3 plus V6, which, as we just saw, we just have to keep there, minus V4, which is, now V4 would be R4 times this current, if you call this I4. So minus R4 times that current. But the current I4 itself, little I4, is in terms of mesh currents, big I4 minus big I3. And finally, the last equation, V7, which again we have to keep as is, plus V4, which is plus R4 times I4 minus I3, minus V5, which, if you call this I5, V5 is simply R5 times little I5. But what is little I5 in terms of mesh currents? It's minus big I4. It's just that the way I have defined the directions, it just happens to be that little I5 is the opposite of I4. And there is no other mesh that R5 is part of, so that's all I have. So these are my KVLs written in terms of mesh currents. Now, you could have done this directly without the intermediate step of defining those little currents and repeating what I did every time. And that's fine once you have enough practice and experience. Okay? For the first few problems, please make sure to do these intermediate steps of talking about element currents and relating them to mesh currents explicitly, and then replacing. That little amount of extra ink and paper spent, which actually you don't even do because most people are writing on their tablets, I see. So it's that little amount of extra electricity that you use in that will pay dividends over time. Okay? So do it explicitly a few times until you feel really comfortable writing it directly in one shot. But the goal ultimately is that you will be able to do it eventually in one go. Okay, so these are my KVLs. And let's see, I have 4 unknowns that are the 4 mesh currents, I1 through I4. But I also have 2 other unknowns, V6 and V7, which I could not directly relate to mesh currents. But as I said, the current sources, which created this obstacle to begin with, make up for it by now providing us with some additional pieces of information. What is that? Well, it's the current in a current source. Let's look at this source I sub s up there. What that element is saying there, if you want the element relationship for it, is the current in that branch is IS going from right to left. Now, IS could be a positive or negative number. That's the current. Is there a relationship between that current and mesh currents? IS is exactly I2 minus I3, precisely so. The same way that we dealt with all the other element currents, well, the current in IS, thinking about it in terms of the mesh currents, is big I2 minus big I3. So these are my KVLs that I have from above. But additional info, the current IS is, what was it? I2 minus I3. And now let's look at the other source. The current in this other source, which happens to be a dependent source, that's alpha V4. So alpha V4, which is a current, if you look at it, in terms of mesh currents, is going to be big I1 minus big I4. But what is V4 itself in terms of mesh currents? We talked about this before. V4 in this circuit happens to be R4 times big I4 minus big I3. So you can write this like that. You see, V4 is R4 times big I4 minus big I3. And so that is there you go. So you have 1, 2, 3, 4, 5, 6 equations with unknowns I1 through I4 and little v6 and little v7. 6 equations, 6 unknowns. All is good. These are your mesh analysis equation. Now, if you wanted to do computation and be efficient, you would want to simplify, order things, and put them into a matrix form. So let's do that. So the next step is simplify and organize. So in the first equation, I have R1 plus R3 times I1. And then minus R1 I2 minus R3 I3 minus V7, which is an unknown. And then the known quantity there, Vs, which was a parameter of the problem, I'll bring to the other side. Big Vs. That was just the voltage of the source. And by the way, when I say known versus unknown, of course, in a given problem, you could give me a mesh current and say Vs is unknown. You know, work the other way around. But so it doesn't matter. But in this case, let's assume you know Vs and you're trying to calculate mesh currents. So that's the first equation. The second one, you'll see minus R1 I1 plus R1 plus R2 I2 minus V6. Equals 0. Did I get that right? Minus R1 I1 plus R1 plus R2 I2 minus V6 equals 0. The next one, I have minus R3 I1 I don't have I2, so that's 0 times I2. And then I have plus R3 plus R4 times I3. And then I have minus R4 I4 and finally plus V6 equals 0. The fourth KVL, I have 0 times I1, 0 times I2, minus R4 times times I3. Plus R4 plus R5 times I4 plus V7 equals 0. And please verify that I'm doing these correctly. And then another additional piece of information I have is this equation at the top here, I2 minus I3 equal IS. IS being the current in the current source, presumably a known quantity. And then finally, in the other equation there at the bottom, I have I1 minus R. Yeah, so I, depending on which way you want to move things, let's say I1 plus alpha R4 I3 minus 1 plus alpha R4 I4. And again, alpha is a parameter that we know. Did I do that correctly? Minus I4 minus alpha R4 I4. There you go. So these are the 6 equations written in a nice way, which then in very much the same manner as what you did for nodal analysis to put things into a matrix form, you can do the same thing exactly here. So put in a matrix. A matrix equation. So I have to have 6 equations represented, which means I need a 6 by 6 matrix, a vector of unknowns that has my 6 unknowns, and on the other side, a vector of the source values. And so let's just do that. So this is my vector of unknowns. I1, I2, I3, I4. I think V6 and V7 is what we had. These are my unknowns. And my matrix then is going to be a 6 by 6 matrix. The elements for the first row will be R1 plus R3 is the first element, then minus R1. Sorry, is it R1 plus R3? Yeah. And then minus R3. Then I need the coefficient in this equation for I4, and that's 0 because I4 doesn't exist in the equation. So it's like you have 0 times I4. The coefficient for V6 is similarly 0, and the coefficient for V7 is minus 1. So 0 and minus 1. So you can verify that if I take this row and multiply by the column of the vector, I'll get the left-hand side of my equation up there. And I'll leave it up to you guys to double check that is correct. And this then has to give me what's on the other side of the equation for the first equation, which happens to be Vs, big Vs. Okay? And so for the second line, then I have minus R1, then R1 plus R2, and then for I3 and I4, they don't appear, so their coefficients is 0. But I have minus 1 for V6 and 0 for V7, and on the other side there is nothing. Again 0. For the third equation, minus R3 for I1. For I2 I have 0, and for I3 I have R3 plus R4. I'm looking at the third equation. Then minus R4 for I4. And then I have 1 for V6, and then 0 and 0. Fourth line, minus, so there's 0 for I1 and I2. So the first two elements of this row are 0. Then I have minus R4 times I3. R4 plus R5 times I4. Zero for V6 and 1 for V7, and 0 on the other side. Okay. For the fifth row, I simply have 0, 1, minus 1, then 0 for R4, V6, and V7. And on the other hand, on the other side, sorry, I have IS. And for the final equation, I have 1 for I1, 0 for I2, alpha R4 for I3, minus 1 plus alpha R4 for I4, and then 0, and then 0. And on the other side, I also have 0. So if you call this unknown vector, vector of unknowns, so let's call this a big vector I. This is the matrix of parameters. And then this is the, so let's call this maybe A. And this, let's call it vector due to sources. So your equation is A times I equals S. And so to solve this, I is A minus 1 times S. And again, I rely on what you saw in linear algebra. But this is it. So if you were to program this into a computer, all you had to do was to figure out how to write this matrix, and then ask the computer to calculate the inverse matrix. And then that's a simple multiplication of that by the vector that originated from the sources in the problem. And then it will give you the vector of unknowns. And of course, if you then wanted some other quantity in the circuit, such as any of the element currents or voltages, then so let's say if you're interested in little I3, now that you have big I1 and big I3, the difference of those will give you little I3. If you want little V3, well, that's little I3 times R3. Or if you want the power in that element, then you have its voltage and current. So you can then work out everything else that you want in the circuit. So this is mesh analysis. And again, including a situation where you see that there is a couple of current sources that create a little bit of a pause maybe. And at first you might think, oh, how do I relate their voltages to to mesh currents? But then you see immediately that they give you these additional pieces of information. So additional equations that, granted, make your problem a little bigger, but That's fine. And again, as you see, similar to what you saw in nodal analysis, the matrix is not too bad. It's relatively sparse. And that's because of the fact that if you think about where each equation comes from, that's a KVL. And each KVL contains only a few of the elements, typically, right? So it doesn't contain all the elements. And so it doesn't have all the mesh currents in it. And hence, a lot of the zero coefficients in the matrix. And that's good from a computational point of view. Again, it would be an interesting exercise for those of you who are interested in writing code to go write a circuit solver using mesh analysis. Okay? And this is really where the utility of these methods lies, because you have a systematic approach. I'll just draw your attention to one little fact here that maybe even shows perhaps more obviously why this is appealing from a coding point of view, a circuit solver point of view. And that's this. If you look at this matrix, do you observe any pattern? Let's look at the diagonal elements. So on the first row, first column, which is the coefficient that multiplies I1 in the first equation, I have R1 plus R3. R1 and R3 happen to be the resistors that are part of mesh 1. And similarly, you will see element 2, 2, the other diagonal element, and that's the coefficient of I2 in the second line, in the second equation. And that has R1 plus R2. If you look at mesh number 2, it has R1 and R2 in it, and so on. So you see that there is potential there to really do a pattern recognition and program this into a computer code. Okay. What creates a little bit of a problem is the current sources, which kind of introduce these equations that don't follow the same pattern. But with going through a few examples like this, you can figure out how to include those in your code, right? So I mean, the code will be the recipe will be a little more involved than just the simple diagonal and off-diagonal elements, depending on resistors. But you can still do it. Okay? So this is really what makes these very appealing. It's something that we are going to use occasionally to analyze circuits. It's not something that I want us to rely on, similar to nodal analysis. Depending on the type of circuit that you deal with, and we will see this especially when we talk more about electronics, you will see that in some cases it's more insightful or convenient to explicitly write your KVLs and KCLs directly. In some cases, it will be easier to use nodal analysis, or more convenient, or more insightful. And by the way, sometimes what is convenient is not necessarily more insightful in general. In some cases, mesh analysis. So here's a simple example. If you have a circuit that has a couple of nodes and many elements connected between them, so you have many, many meshes, but only a couple of nodes, would you use mesh analysis or nodal analysis if you had the choice? So if you have 10 elements in parallel connected between two nodes, right? If you wanted nodal analysis, basically one node would be reference, the other one would give you, one KCL that will give you the node voltage. If you wanted to write mesh analysis, you would have how many? 9 meshes, a 9 by 9 matrix, right? Conversely, if you had a circuit that had just one big loop that had 20 elements around it, well, if you want to solve for all the node voltages between those, you'll end up with a huge matrix, right? It's not going to be a difficult problem, but it's going to be bigger. Whereas you could write one mesh equation, find the mesh current, and then from that, and of course, ultimately, you would, if you want all the element voltages, ultimately you have to work backward and find those. But depending on how many nodes you have versus how many meshes you have, one approach would be computationally maybe easier, at least at the first step. So this is it. Let's take a short break, and then I'll just write down the key elements of this recipe that I mentioned. So let's take a 5-minute break. So starting the second half, and like I said, we covered what was really important. Now I just want to give you that little recipe that I mentioned. And so this is what you would call nodal analysis by inspection, or mesh analysis by inspection. By inspection, meaning that you can do it directly by looking at the circuit, inspecting it. And we will look at a special case of this, a limited case of this, for when all the sources in the circuit are independent current sources. Okay, for the simple reason that, as we saw, if in nodal analysis, if you had voltage sources, dependent or independent, that you would have those extra variables for which you had the extra equations coming from the information of the voltage sources, which makes things a little more complicated. And not that you can't deal with it as a matter of coming up with more steps in the recipe. But here I want to show the simple case that's really a simple recipe for us to see that. Okay, so basically this is what your equation will look like. If you have only independent current sources, all your unknowns in nodal analysis will be node voltages. So let's say you have V1, V2, until Vn. So let's say you have n plus 1 nodes, one being the reference, and so you have n unknown node voltages. And so your matrix will look like this. If you go back to the examples we did yesterday and before on nodal analysis, you saw that on the diagonal, you would end up with the sum of the inverse of the resistances that are connected to that node. Okay? So let me write this down, and you'll see. By the way, G is sometimes used for conductance, and conductance is just inverse of resistance. Okay? So your equation will look like this. And so on. And on this side, you would have these known currents. And the value of these are like this. V1 till Vn, these are unknowns. GKK, or maybe let's say, yeah, I don't want to use I, so yeah, GKK would be the sum of the conductances connected to node K. So G11, for instance, would be the sum of the conductances connected to node 1. So all the resistors connected to node 1, the inverse of each of those is the conductance for each of those. And so the sum of those would be GKK. To node K. And conductance, remember, is simply inverse of resistance. Okay, that's an interesting or important concept to remember. Conductance is just inverse of resistance. GKL, let's say, so the off-diagonal elements, so G21 or G35 and so on, is the sum of the conductances directly connecting node K and L with a negative sign. So negative of the sum of the conductances directly connecting nodes K and L. And remember that K and L are different. So I'm talking about off-diagonal elements. We already talked about the diagonal elements up there. V sub K is the unknown voltage at node K. And now if you go to the right-hand side, which originates from the current sources, from the independent current sources, so for each row, so IK, that's the sum of all independent current sources directly connected to node K. And you have to be very careful, because when you talk about the currents connected to a node, there is the matter of the directions of the currents to deal with, right? In this convention, with currents entering the node treated as positive. This is it. So basically, you can look at the circuit and write the matrix equation directly. And so this is really the algorithm for a program that you can write. And it will solve any circuit that has resistors and independent current sources. And I'm sure you're going to find it easy to program, right? Again, as I said, well, if the circuit has dependent current sources or voltage sources, there's that additional piece of information that you have to put in. And I'm not too keen on developing a bigger recipe for that. I don't expect you guys to memorize this recipe, for that matter. So what I really care about, which is I think what you want to be able to retain really, is how to write your nodal analysis equations from scratch and then put them into a matrix form. But this is a pattern that I hope you will recognize after just solving a few examples. And so what I'd like to ask is that now you go look at the nodal analysis problems, examples that we did, and see this recipe, how it manifests itself there. Yesterday, we also talked about the issue of signs, right? So, of course, you can take all your equations and multiply both sides by -1. Excuse me. So you could equally well have said GKK is the negative of the conductances, the sum of the conductances connected to node K, and GKL is the positive of the sum of the conductances directly connecting nodes K and L. And IK is the sum of all dependent sources current sources going directly into node K, with currents entering the node treated as negative. Right? You could have said that. But so here's the other way around. This is the way I've seen people talk about it. Again, I don't expect you to memorize this. If I ever want you to do things by inspection to show that you can follow this recipe, okay. Yeah, I won't expect you to memorize it. So very good question. What if I call this node over here node 1, and you call this node over here node 1, right? So your matrix is going to look different, and your vector of solutions is going to look different. But ultimately, when physically we go to, say, this node here, for me it's V1, and it will be the first number in my vector. For you, it will be V5, and it will be the fifth number in your vector. So the physics will be the same. Okay? So this does not imply that the matrix is exactly unique, right? But it implies that it will give you a unique physics at the end. Okay? So again, I think this is something that I'd like you guys to give a try on your own. Just think of it as a small exercise. And similarly, now I'll go a little faster and write the mesh analysis recipe for this special case. And basically we talked about it briefly, so I just want to write it down. But you see R1 and R3 there, you had the sum of the resistances in mesh 1 on the diagonal element. And then you had the negative of the resistance that was shared between mesh 1 and 3 there, R1. Sorry, between mesh 1 and 2, that was element 2, 1, and so on. So mesh analysis by inspection. Again, limiting it to when all the sources in the circuit are independent voltage sources. And so here, instead of the inverse of the resistances or conductances, you see the resistances themselves. And you have your vector of unknowns, which is I1, I2, through to IN. And then the vector that comes from the voltage sources, N. And here you have the elements of the matrix R11, R12, till R1n, R21, R22, R2n, and so on, Rn1, Rn2, Rnn. Okay, so a very similar pattern to what you had there. These are the unknown mesh currents. So if you have n meshes in the circuit, you have n of these, and this is the vector due to voltage sources. And then to populate this matrix, the recipe is like what we just discussed. So R K K, so a diagonal element, is the sum of the resistances in mesh K. As you go around the mesh, all the resistances you encounter. And the off-diagonal elements, RKL, is the negative of the sum of the resistances that are shared between meshes K and L, that are part of both meshes K and L. And remember that K and L are two different meshes, right? K and L are not equal. For the case they're equal, namely the diagonal elements, we have already talked about it at the top there. And so the IK is your unknown mesh current for mesh K. Okay, so that's a mesh current, right? Not an element current. Now, by the way, which direction? For this recipe to be consistent, you have to define it clockwise, okay? Because then we'll say, just to have a full recipe, Vk then is the sum of all the voltages that you have in mesh K. And in the example we did up here, you saw an example of that. You had Vs, and Vs was, well, it happened to be the only voltage source you had in mesh 1. It's up here. So anyway, so Vk is the sum of all the independent voltage sources in mesh K. And again, to be self-consistent with recipe is, if you go clockwise, a voltage rise is treated as positive. A voltage rise in the clockwise direction. Okay? Again, nothing magical here. Just look at the couple of mesh analysis examples that we've done and see to what degree you can apply this recipe, and make sure that I'm saying things correctly here. Okay? Just treat that as another little exercise. So, and you know, you can really take a very small circuit. I did a small one last time, so go back to that lecture and do that with inspection, see how far you can get, right? Following the recipe, and make sure that I wrote things down correctly. Any questions? Anything you guys would like to discuss a little more here? So I'm very happy to say that this formally concludes what we wanted to cover in terms of nodal analysis and mesh analysis. Again, the emphasis being to be able to do them from scratch. Okay, that's really where the value lies. Okay, so I think that's it.